Okay, so we're taking take 2 of today's lecture. So the recording crashed in class today. So I'm going to quickly, well, not quickly, I'm going to run through the material again. It'll be a little faster than in lecture because there's no questions or anything that are interrupting. But let's go back. I want to sort of just remind you of where we were. We were talking about the role of vacancies. And that the nucleation of these fine zones are strongly influenced by the presence of a significant vacancy population. And we can see here we've got two different materials. If we quench from this point here, L, from the alpha region into the two-phase region down here below the GP zone solvus, we end up going through heterogeneous nucleation, mostly at grain boundaries and dislocations, and we have about 1 million precipitates per cubic centimeter, which is not useful for strengthening. But if we go from this higher temperature down into the two-phase region, we have roughly, why is this going ahead, 7 orders of magnitude higher precipitation density, and that's completely due to the fact that we have a much higher quenched-in vacancy content. So where does this come from? We reminded ourselves that vacancies don't pop into existence out of nowhere. If you want to form a vacancy in the middle of your crystal, you have to move an atom to an interstitial site, which is very expensive. But at interfaces, free surfaces, grain boundaries, certain dislocations are basically vacancy sources and sinks, where we can easily create a vacancy. The enthalpy of formation is about 0.7 eV, and we also went through that we have a equilibrium concentration of vacancies, which is the balance of the enthalpy term, which is the number of vacancies times the enthalpy of formation, and the change in entropy. And the minima of this, the minimum free energy, is our equilibrium vacancy concentration. Here I go through it and I include a vibrational entropy term, right, which is the change in vibrational entropy in the atoms that are next to the vacancy sites, right? And that our vacancy concentration increases exponentially as we approach the melting temperature. Okay, so why do vacancies influence nucleation, right? So on quenching, right, the significant vacancy supersaturation can be retained in the material, right? Remember, vacancies move by atomic jumps, so you need enough thermal energy for the vacancies to diffuse through the material. The excess vacancies can't be annihilated easily. They have to be annihilated at sinks, right, which are, again, our surfaces, grain boundaries, dislocations, right? If we don't have a lot of sources or a lot of sinks when we quench down, these excess vacancies are available to assist our nucleation processes, right? They're going to greatly affect the local diffusion, and they're also going to relieve the stress fields, the strain fields around larger atoms. So in aluminum, silicon, or germanium, right? And it is that reduction in strain is going to give us a reduced activation energy for the formation of GP zones. Okay. So then the last thing on Wednesday was a quick calculation that showed if we estimate the diffusivity from looking at the distances between GP zones, we end up with a diffusivity that's around 10 to the minus 16 centimeters squared per second. If we then actually calculate the diffusion of from tracer diffusion of copper and well annealed aluminum, we have a diffusivity that's 2 orders of magnitude lower, right? And this change in diffusion is completely due to the presence of vacancies, right? So for some aluminum copper alloys, depending on the composition, right, they can age at room temperature. 2017 is an example of an alloy where this happens. This would be completely impossible without the enhanced mobility due to the vacancies. And so a key point that we want to get across is that in general you need a critical supersaturation of vacancies for the nucleation of GP zones. And the critical concentration is a strong function of your aging temperature. Right, so why is this? Well, the higher the temperature, the faster your diffusion. Right, so eventually you get to a high enough temperature where your mobility is great enough that you don't need the excess vacancy concentration. But at lower temperatures, you do, right? So if we age at 130, you are going to have a finer, more even distribution of GP zones. If you age at 190, you're going to have larger in scale with a greater separation between particles with more coarsening. Okay. Right, so if we think about what happens, right, the presence of vacancies is not going to affect our surface energy term, at least not as a first order effect. It's also not going to affect our bulk equilibrium free volume concentration, but it can have a profound effect on the strain term, right, which is going to move this curve down, right, which is going to move our critical radius smaller, and our activation energy is going to increase. Our activation energy is going to decrease as our critical radius gets smaller, making it easier to nucleate if we can reduce this strain term. So we have a couple different types of aging treatments that commercial alloys go through, and we'll talk about the specifics for specific alloys when we get to the commercially relevant alloy section. But for right now, we can just break it up into 3 general types. So the first, where we quench from to a temperature that's above the GP solvus, and then we age at a temperature that is above the GP solvus. And this is usually used in alloys that don't have a lot of age hardening potential, right? So for example, in aluminum magnesium, it's very difficult to form a very finely dispersed precipitate structure. And so we want to keep them really closer to the solid solution state. Also, in magnesium, if we're under 5 weight%, the GP solvus is going to be below the room temperature, right? We can push up the GP solvus by increasing the magnesium content, but as we'll show later, that bites us because that leads to beta formation on the grain boundary and loss of ductility and decreased resistance to corrosion. So then the second major heat treatment is alloys that are quenched to below the GP solvus and then aged below the GP solvus. So this is aluminum mag silicon alloys, the 6000 series alloys that are very important. And why the heck? And this right here allows us to nucleate um, a very fine scale of GP zones, and in this particular alloy, they form as rods along the 100 axis, and then they serve as heterogeneous nucleation sites for theta prime, theta double prime, theta prime in the equilibrium phase. And then we have a third type, where we quench below the GP zone solvus and then age above. And this is really what we do for most age hardening systems. And really what we're doing is we want to first nucleate a very, very fine dispersion of GP zones that serve as heterogeneous nucleation sites for the strengthening phase that we're actually interested in. So really this is more of a duplex heat treatment. We quench, we'll hold below the GP zone solvus for a very short time, and then raise it up above the GP zone solvus to nucleate the phase that we actually want. Okay. So all alloys involving strengthening by dispersion of very fine second phase particles, we tend to see these regions near the grain boundaries that are denuded of precipitates. Right? We call these precipitate-free zones. They're largely unavoidable, although we can change their structure to some extent. Right? And these come about really from two different factors. The first is, we had mentioned several times that we need a excess vacancy concentration above some critical value for nucleation to occur. But grain boundaries are one of the best sinks for vacancies, so those vacancies can easily diffuse out in regions near the grain boundaries. So if we look at the excess vacancy concentration, we see a distinct profile as we approach the grain boundary, right? And this can be below the critical value. And so on aging, we get precipitates that form out here, but none that form near the interface. So the other thing is we also see a dip in the solute concentration near grain boundaries, but it's much less than the dip in the excess vacancy concentrations. And in class, I asked everyone to think about why you would have a slight decrease in the solute concentration near the interfaces, and to discuss amongst yourselves. So here we see the region that we're below the critical vacancy concentration for GP zone formation. This is going to be the precipitate-free zone, and that the quenching rate is going to have a profound effect, right? The faster we quench, the less time there is for vacancy diffusion, and the thinner the precipitate-free zone is going to be. Whereas if we slowly quench it, we're going to have wider. And if we quench it extremely slow, we'll remove all of the excess vacancies, and then it'll be very difficult. We won't have any GP zones form. We'll have to hold for very long times to nucleate the thermodynamically stable phase. Also, we can have a depletion of solute near the boundary because of diffusion of solute to the boundary where large particles are going to form. I mentioned the magnesium, we form grain boundary beta rather than easy GP zones, right? And so we have the here we have a precipitate at the boundary. Now we have a solute dip. Because of this precipitate here, we had to diffuse material to grow this precipitate, and so we have this concentration profile that looks like this. And this happens, in this case, our critical solute that we need for nucleation of GP zones falls below the critical value. Our solute concentration falls below the critical value required to nucleate particles faster than our excess vacancy contribution falls. So we have a wider precipitate free zone due to the presence of secondary phase formation at the grain boundary. And we see this here. This is aluminum zinc mag, and we can see the very large precipitate free zone with these fairly coarse particles attached to the grain boundary. Right? And trace elements can also have a very profound effect. Here's our aluminum zinc mag again. If we add a small amount of silver to that, we essentially eliminate the precipitate free zone. Right? This is not easy to predict when this is going to happen, right? These quaternary and multiple alloy compositions, all the reactions that occur, the phase diagrams get exceptionally complicated, and it's not always easy to determine when situations like this are going to happen. But the takeaway is that trace elements can have a very profound effect. So the factors that influence the precipitate free zone formation, right? Interaction of the solute with vacancies, right, is going to reduce the effective vacancy concentration and reduces the rate of nucleation in GP zones. We just saw that. In other cases, in aluminum copper, if you add cadmium, indium, or tin, it will greatly reduce the rate of nucleation in GP zones. Right? We can raise the GP zone solvus temperature. So if we change our alloy compositions and we alter the range of the temperatures over which phases are stable, right? If we add some silver to the aluminum zinc magnesium system, we saw that on the previous slide, right? The precipitate free zone is drastically reduced by the raising of the GP solvus by the addition of the silver. Right? So here we look at the increased undercooling, right? And remember, undercooling is essentially the driving force. And so with the trace solution, right, we've raised our solvus, so now we have a greater degree of undercooling. We have a much greater driving force for the nucleation of GP zones than we would if we didn't have the silver in there. And then influencing nucleation of existing precipitates by reducing the interfacial energy, right? This is where tin and aluminum come in, and we can promote the formation of a different precipitate altogether. So the big takeaway here, right? Here's the exam question, right? So precipitate free zones we can alter substantially by, we can add trace elements and screw with everything that we just talked about on the previous slide. We can change our temperature, how fast we quench. We can change our aging treatment, our aging temperature, or our quench rates, right? And so this is what we can do to alter the precipitate free zone, right? And our shape, and looking at the specifics of the heat treatment, right? Here we are, this bullet point right here, the same aluminum copper, and here this is aging at 130, Over here we see aging at 190, and if we look at the 4.5% copper, we tend to age very slowly, right? We have to hold for about 30 days before we reach our maximum hardness, in this case roughly 130 Vickers hardness. Now compare that to aging at 190 days. We reach our peak hardness in less than 1 day, but we don't go as high. We have slightly more than, say, maybe 110 Vickers hardness. Here we have almost 140 Vickers hardness. But again, it's not practical to age an alloy for a month before we use it. So what makes a good hardening system? A couple times over the course of this bit, I talked about the Solvis line curvature, right, or how turned over the phase diagram. The Solvis line is on the phase diagram, right? We talked about homogeneous nucleation of a fine dispersion versus heterogeneous nucleation at defects that lead to a coarser precipitate structure. And then how hard the heterogeneous precipitation on dislocations and grain boundaries, and I'll add on other intermediate phases there. So let's look, we've talked a lot about aluminum copper, the binary, as being a sort of the archetype composition for this for age hardening. And we talked about the sequence from GP zone to theta double prime to theta prime to the equilibrium theta phase. Let's take a look at some other alloys. I briefly mentioned aluminum mag, right? And if we look at the phase diagram, we have a very strongly curved Solvis line, right, with about 16% solubility of magnesium and aluminum at 450 C. However, our GP zones are spherical in shape, right? They're not platelets like in aluminum copper, and also the GP zone Solvis is below room temperature for alloys that are of interest. What do the intermediate phases look like? Well, we have a beta prime hexagonal structure, right? And beta prime does not resemble the FCC structure of aluminum at all, right? So the structure is incompatible. So we nucleate beta prime heterogeneously, mostly on dislocations and grain boundaries. It's a little more difficult to nucleate on the GP zones. And we have an orientation relationship that looks like this. So the basal plane in hexagonal is parallel with the cube plane in the alpha, the FCC phase, and the O1 bar 10 direction in the beta is going to be parallel with the 110, the face diagonal in the FCC. And I threw a note in here, said this is the orientation relationship like this is going to implies that this is a semi-coherent interface, and I asked the class to think about this and maybe sketch out some of those lattice planes and atomic positions and figure out why I speculate that it's semi-coherent. The stable phase is the beta phase, and depending on what paper you look at, it's either going to be listed as Mg5 aluminum 8 or Mg2Al3. Earlier papers determined the crystal structure and the composition incorrectly, right? And this is back to a FCC type structure, right? And the lattice parameter is 2.824. Why is that significant? But think about it with respect to the lattice parameter of plain aluminum, and it might make a little sense. If not, ask. So the beta phase is going to heterogeneously nucleate as lazar plates, primarily at grain boundaries, but it can also nucleate at the surface of the beta prime particles. It's an incoherent, and it forms generally with the orientation relationship given here. So aluminum mag is not particularly useful for age hardening, right? We have no pathway, no processing pathway to get a nice, stable, fine dispersion of particles that we need for strengthening. So why do we still alloy with magnesium? And so magnesium in solution provides very good solid solution strengthening, right? We do get a significant reduction in density, and unlike copper, magnesium in solid solution does not strongly affect the corrosion properties. So therefore we use it commercially. The downside is we can form grain boundary beta and sensitize our alloy and lead to weakening in properties. And for this reason, we want to keep the magnesium content below 3 weight percent because we don't want to nucleate and grow beta on the grain boundaries. This serves as a crack nucleation site. This is a brittle compound, and it's also gives rise to intergranular corrosion problems. Okay, so what about if we add a little silicon in there? So now we go from aluminum magnesium to aluminum magnesium silicon, and this is the 6000 series of alloys, right? Exceptionally important commercial series of alloys. We'll go through several alloys, several specific alloys in upcoming lecture. But if you have an aluminum frame bicycle, it's probably 6063, right? And very important automotive alloys as well. So unlike pure aluminum mag, GP zones here form needles along the 100. The GP solvus is higher than normal aging temperatures. We do have some intermediate phases, magnesium to silicon, hexagonal structure. It forms coherently, and it nucleates from the GP zones. Aha! So that's one distinct difference from aluminum mag and aluminum mag silicon, is the fact that we can now nucleate these other intermediate phases on the GP zones. Means that we have a much better shot of getting a nice fine dispersion. Right? The stable phase is beta, right, with an FCC crystal structure, right? And this forms as platelets on the 100 alpha planes, and it often nucleates directly from the beta prime, right? So in this case, the silicon changes our precipitation sequence. Instead of our second intermediate phase nucleating heterogeneously from grain boundaries and dislocations, now we can nucleate on the GP zones, and this leads to a different class of magnesium alloys with very different properties. We'll talk about specific alloys a little bit later. Right? So moving on, the other important family is aluminum zinc. Right? So again, we have our highly curved solvus. Zinc is the only other compound present on the phase diagram, so we're not, whereas with aluminum mag silicon we had a intermetallic, the the Mg2Si intermetallic compound. Right, but we do have something odd here, right? We've got alpha and alpha prime. What's going on with this region here? Right, and so this is actually, we have a miscibility gap, and then we have a spinodal decomposition, and the alpha prime phase is actually an incoherent phase with a rhombohedral structure, and it occurs at starts to occur within this range of 60 to 70% weight percent zinc. Or, sorry, atomic percent up here. Right, so we have to keep this in mind with aluminum zinc. But we have a precipitation sequence that starts with GP zones. In this case, the GP zones tend to be spherical and ellipsoidal. So we have a misfit of strain of only about 3.5%. So that's why we get this this shape. The intermediate precipitates are rhombohedral, right? And we end up with coherent FCC matrix, but incoherent with the alpha prime. Okay, so we can form a refined dispersion of spherical zones, spherical GP zones, and this misfit strain, right, is enough to give us significant hardening, right? Remember, our dislocation interactions with the strain field around GP zones is what gives us hardening in that case. So if we add a little magnesium, now we have aluminum zinc mag, right? These are the 7000 series of aluminum alloy, which offers really great potential for hardening. Again, we have spherical GP zones, right? Aluminum mag, the spherical GP zones were not great. Aluminum zinc, the strain associated with them was enough to give us hardening, right? But the key thing here with these aluminum zinc magnesium alloys, the 7000 series, is we have a huge number, a bunch of intermediate phases. We have 3 intermediate phases, the eta prime, eta, T prime, and T, and we go from FCC to hexagonal, 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 back to cubic, cubic with a very with a lattice parameter of 1.42. Remember, aluminum is 1.43, so we have a very small misfit in the thermodynamically phase, right? The eta prime phase forms from GP zones, right? The eta will form from the eta prime. The T prime phase is semi-coherent, and depending on the composition, it may heterogeneously nucleate, may form instead of eta, right, in alloys with high magnesium zinc ratios, right? Okay, aluminum lithium. So aluminum lithium is really of great interest because lithium has a really big effect on the modulus of aluminum. Right, we get both significant effects from substitutional solution strengthening and from precipitation strengthening. So we end up with very stiff alloys, and we also have a very significant reduction in density. So what the heck is going on here? So end up being very important class of alloys for aerospace. Jesus. Okay. So if we look here, the stable phase in equilibrium with aluminum is delta, right? So most of the time we're going to be in this two-phase regime with FCC and this delta phase over here. Well, what is that delta phase? Delta phase is a bit complicated, right? It's a B32 structure. It's the same structure that you get for aluminum titanium. And it's this complicated beast here, 16 atoms per unit cell, so it's quite a bit different than FCC or HCP, right? So these differences are going to suggest that we need a heterogeneous nucleation mechanism, right? There's no easy way to nucleate this homogeneously, right? But we can precipitate metastable delta prime phase, right? The delta prime phase, aluminum 3 lithium, is the L12 crystal structure, and we have a small misfit, not 0.08%. So a good fit structurally. This allows us to nucleate homogeneously, a very refined dispersion of precipitates, and then subsequent aging, these particles will coarsen and grow, right, by Oswald ripening, right? Remember, Oswald ripening is the particle coarsening, where small particles will shrink and large particles will grow, and this is a direct consequence of Gibbs-Thomson. Remember, the smaller the radius, the smaller the radius of the particle, the greater the free energy of the particle, and the kinetics for Oswald ripening goes as the difference between the cube of the current particle size and the initial particle size, right? Remember, right? Oh, what is PowerPoint doing to me? Okay, so the delta, this is the delta prime solvus, right? There's a lot of confusion in the literature over the exact location of this solvus, and basically that's because we can get either coherent or incoherent nucleation. Incoherent, we nucleate on the dislocations. Coherent nucleation on the grain. So depending on what the interface is like, the particles will dissolve at different temperatures, right? And this difference is going to be a function of the small strain produced by the particles, right? So since the misfit is so small of the delta delta prime, there isn't a huge driving force from the surface energy term to force it to nucleate a specific way. So if we look at just quenching this is aluminum 12.9% lithium. We have end up with a very refined dispersion of delta prime particles, right? This is as quenched. This isn't aged. On subsequent aging, we're going to grow by Oswald ripening, and we see that we have a coarser, more widely separated, but still fairly uniform dispersion, right? We can also grow delta particles on the grain boundaries and dislocations. Right, on aging, we'll also grow stable delta at the expense of the delta prime dispersion, and of course, we end up with the formation of precipitate free zones. I think this is that's what it is. It's the mouse. Anytime I bump it, for some reason, it is driving back and forth. All right, so we end up with, here we see a precipitate-free zone, right? In a recrystallized aluminum lithium alloy. This has been aged for five days. So much like the other alloys, right, we're potentially nucleating the thermodynamically stable phase by a heterogeneous nucleation. We're growing the thermodynamically stable phase at the expense of the intermediate particles. We're forming a precipitate-free zone near the grain boundaries. We also have a potential cellular coarsening. But this is a very low driving force for this. The energy is very low. So this is, I don't want to spend a lot of time with it because it ends up not being a particularly important mechanism, but we can have coarsening of the precipitates into a cellular structure. Okay, so I mentioned before that aluminum lithium is important because of the huge modulus effect. All right, and so here we see the solid solution strengthening that occurs. All right, so we're in this regime here, in this alpha plus delta prime, and this is the contribution of solid solution up to 14% lithium from solid solution strengthening, right? And with and without the addition of magnesium, you can see that's a fairly dramatic increase in stiffness, right? But then if we add the effect from the delta prime, the volume fraction of delta prime, we get an additional boost, right? So we can end up with a roughly a 50% increase in modulus with the addition of lithium to aluminum, which is huge. I should plot this also with the change in density with the addition of lithium. So we end up with a lighter, stiffer alloy, right? And if we're doing elastic design, we very much want nice, stiff trusses and structural members. All right, so just a quick review on aluminum. Lithium, right, so the reactivity of lithium might potentially cause us processing problems. We get a decrease in the density by 3%, by 1 weight percent of lithium added to the alloy, right? It behaves very much like other alloys. We have to worry about overaging, general coarsening, and the formation of precipitate-free zones, right? And all of these can contribute to a reduction in strength and detrimental to other properties such as toughness. So then the delta prime precipitate structure offers a lot of hardening dislocations, but they can be cut by dislocations. Why did it went back right to where we were? If I didn't have to leave for travel, I would re-record this, because this is sort of confusing with it bouncing back and forth. I'm sorry. But we have the delta prime precipitates are cut by dislocations, and just like the aluminum copper, when the dispersion is fine, remember every dislocation we cut, we reduce the cross-sectional area of our particle by by essentially 1 Burger's vector, right? And this gives us a localization of slip can cause a softening issue. Okay, so starting Wednesday, we're going to talk about strengthening mechanisms other than hardening, and then on to Friday, we will start going through the alloy systems one by one through the commercially relevant alloys, to wrap up what we're doing on aluminum. So we'll finish up aluminum next week. Okay, thanks.